Started recording. So good evening all. I just want to show or tell my introduction again as I forgot to recording it. I am Gangadhar Venkatramana from the Department of Aerospace Engineering. We are trying to solve few questions in the NPTEL session of Fundamentals of Aerodynamics. So before starting this session, do anyone have any comments like that on this course? I should know like that you are experiencing, or can I proceed? I will give you just a minute for your time if you want to share anything regarding your experience of taking this course and how you are doing like this. Like, okay, fine. So now let's start with the first question. Yes, Arun?
Sir, will the recorded video be available on the site?
Yes. Recorded video will also be available, but not on the site. We will tell you, like NPTEL team will coordinate with you and they will let you know how and where it is available.
All right, thank you, sir.
So this is our first question. Romeo was standing on the river bank watching the flowing current. After a while, he had an idea and began imagining specific points in the fluid. And when he drew tangent to the curve approximated by matching those points, he got the flow direction. These are referred to as. I just want to know your comments also if you know the answer. Can you please quickly type the answer? Just answer the option or the answer is sufficient. If you have the mobile or whatever the laptop you have in front of you, you can just type the answer if you know, or else we can discuss on this solution also.
Hello. Hello.
Yes,
Sir,
okay.
myself is Jyoti. I need to know one thing, sir. I'm an architect and I get this message in my WhatsApp group that it's a class about urban services. I'm an architect, but this class is about aerodynamics.
This is about aerodynamics. You are in wrong class.
Yeah. Thank you, sir. I'm leaving. Okay.
Okay. So I'm telling you again, this is the fundamentals of experimental and theoretical aerodynamics. And now we are trying to solve the question one. So if you guys know the answer, I just want to see like whether how much you are able to solve, or your idea of background, like whether you are able to understand the question or not, or you are able to understand the things that your professor has been teaching to you all. So just for my understanding, like to teach well, like instead of missing or skipping some basic things, I just want to understand whether you all are able to, like how many of you are good at these things. Okay, fine. So the question, any people in the lobby? Give me a minute. Okay. So the question basically asking you is, Romeo is standing at the river bank. Suppose is this a river, and some person called named as Romeo standing here and trying to see the river bank, watching the flowing current. This is the flowing current, if you assume like that. And he is watching from there at the river bank. After a while, he had an idea to begin imagining specific points in the fluid. Suppose this is one point and this is another point, another point, another point. Like that he is trying to imagine the points in the fluid. And then when he drew tangent, when he drew the tangent to these points like this, approximated by matching these points, he got the flow direction. That means he got the flow direction means these tangents are representing the flow direction. That means at every point, this is how the flow is going on. So I kept the arrows here horizontally. According to the question he referred, at every point, he got the velocity like this. The arrows that you are seeing here. And at the tangent also curve, he just joined all the curvatures. Yes?
Sir, we are not able to see your writings.
You are not able to see?
Only the PPT, sir.
I just
Only
started
PPT.
writing also. Can someone please confirm whether you are able to see my writing or not on the screen?
It's visible.
Visible, right? Okay, yes. Samir or someone, I don't know, you just please log out and log in again. I hope you can see it. So that's how the person is trying to understand, like, what is the specific, what is this thing that this line that the question is asking is, what is this line? That is the line that is representing a tangent at every flow direction. Suppose, for more clear understanding, what is this question saying is, if you have a point here, if you are trying to identify any points here, and if you know the velocity direction, this is the velocity direction at this particular point. This is how you are trying to draw the velocity, or if you know the velocity field at this particular point and you are trying to trace a tangent of every, you're just trying to draw a tangent to all these points. So this is what the question is asking. And what is this specific line? The author or the author is asking, what is this line he is asking? According to the definition, if we see all these definitions of the streak line, streamline, path line, velocity vector, we should see all these definitions before answering this question. I just want to tell those things. Maybe you have already revised these things in the course that is already going on in the week 2. So I just want to tell you that the definition of a streak line is, many people are keep on logging in the, keep on coming to joining the presentation. So please bear with this delay if you are facing. Keep on adding them. So now the definition of a streak line. Suppose the flow is going on like this from this point. Here is the inlet, and if it is the outlet. So whatever the, consider this is a pipe. If you have a pipe here and you are trying to see the flow in the pipe, you can identify by several ways, like identifying the streak lines, streamlines, or path lines. But what is the definition of a streamline? Streak line is, sorry guys, many people are coming. So definition of a streak line is, if you are seeing a point coming from this, suppose a fluid particle is coming from this point at time t0, later on at a time t equals to 1 second, this fluid particle will go at this location at time t equals to 1 second, right? And another second, time t equals to 2 seconds, suppose another particle is coming at the same time, another particle at time t equals to 1 also, some particle will come from this point, right? This will go at some point and it will settle here. Suppose this is at time t equals to 2. At the same time, time t equals to 3 also, another particle will come from this point and it will settle here, or somewhere, any in the random, anywhere in the random of the pipe. So if you join all these particles coming from the same point in the flow field, this is a flow field, and these all particles are coming from the same point in the flow field. And if you try to join all these particles, will give you the streak line. This is what the definition of a streak line means, that if you are just trying to solve all these, you are just trying to locus, you are just finding the locus of all these particles that is coming from the same point at some instant of time, okay? So that is will give you the streak line. So now we are coming to the definition of the streamline. The streamline is, if you are able to know, or if you by somehow you know, like the velocity vector in the flow field like this, and if you draw tangent at all these points, this line is called the streamline. Okay, this is what the definition of the streamline. And for the path line, suppose you have a flow field, inlet flow field like this, and the path line means, if you have a point here at time t equals to 0, this point will go travel like this. That's it. You just find out a particle of fluid in the flow field and just trace that particle along with the time. Just trace the particle along with the time. That will give you the name itself as a path line. So now you understood the definition of streamline, streak line, and the path line. What you need to understand is, what is a velocity vector. Yeah, I think it's not necessary to describe what is velocity vector. So by this time, you guys can understand, like, the solution or the answer of this question is, a streamline. Okay. So anyone have questions on this? What is
Sir,
this?
is there a chat option where we can answer?
Yeah, are you unable to see the chat?
Yeah, I cannot see the chat.
You cannot.
No.
I'm able to send the things. Let me. Now, can you see anything from your chat box?
No. Can you tell me where it will be? Okay, I cannot see it.
It is available in your. Are you using your
I'm using a laptop.
desktop version or
Yeah,
no, sorry, web version? Web version of.
web version. Yeah.
Please don't take the controls. Web version. Maybe you should have. You should have. Can anyone see whether there is a chat available to you or not from your end? If not, maybe the guests, you're all acting as a guest in this meeting, so it's not allowed maybe to the guests also. That's I did not check that. But for my side, I'm able to use the chat.
Okay. Okay, sir.
If you have any question, you can raise your hand. Are you able to see there is option of raise the hand?
Yes, sir. Yes.
Okay, try to raise your hand. I will let you join.
Okay.
Okay. So the solution of this question is, so answer of this question is the streamline. And the second question that we are going to see today, the equation of a streamline passing through 2 comma 2 in the velocity field v equals to y square I minus x j cap. He's trying to take. Okay, someone is trying to play with this. Please don't take the controls at your side if you have the options. Just listen, and if you have any queries, just text, that's it. Or just raise your hand, I will respond. Okay, don't take the controls. Now, question 2. Suppose you have a velocity field v equals to minus y square I cap minus x j cap. This is your velocity field that you are given to you. And the question is asking like, find out the streamline passing through point 2 comma 2. Okay, so what you generally need to do is you have to understand the definition of the streamline, and then you need to understand how the streamline can be mathematically modeled. Suppose, as I said, this is a velocity vector in two-dimensional, and this definitely have the x velocity component and y velocity component, and this is your point, and if you draw a tangent to it, that is what we say as a streamline at that point. So the tangent definition is, if there is any curve or any line, the definition means the tangent, how you find out the tangent, dy by dx. So if this velocity vector and this curve are both tangent to each other, suppose this curve as, if you represent this curve as dx I cap plus dy j cap. If you represent the streamline ds, suppose a small element ds as a dx I cap plus dy j cap, then the tangent is dy by dx. That should be equals to, because these are two a tangent at this point, that should be equals to v by u. So this is how you can model a streamline. Okay. So now you have, what are the components of your velocity field? You have v, small v, I can say this is a small v, not a capital V. This is your capital V equals to minus v square I cap minus x j cap. From this you can write your small, sorry, your small u component is minus y square. Okay, and small v component is minus x square, minus x, sorry, this is just minus x. Okay, now how do you solve this? How do you find out the equation of the streamline? Just substitute the things u components and v components in the formulation that we just modeled. That is dy by dx equals to v equals to minus x and u equals to minus y square. Okay, so this is the basic idea. If you want to understand or if you want to find out the equation of any streamline or streak line or anything, you should first able to understand its basic definition, and then you should create a mathematical model of it. Like as I said, since the tangential velocity vector is a tangential to the curve of the streamline, so I can equate the tangents like dy by dx, it should be equals to the v by u. So I can equate this. That is the definition that we have seen of the streamline. So if you now try to simplify this, you can get something like y equals to some function of x. That will give you the equation of the streamline. How you can do that? Like you can see it is a directly simple mathematical problem, that is a variable separable one. Minus y squared dy equals to minus x dx. And how you can do this? If you just try to integrate minus y square dy equals to minus x dx. This is how you need to integrate. Okay, then what are the limits now? The limits he has already given 0.2 and 2. 2 comma 2. So the lower limit of y is 2 and the lower limit of x is 2 and the upper limit will be y and x. Substitute these limits and solve the integration. What you will get? If you try to solve this, minus y cube over 3 with the limits of 2 comma y is equals to minus x square over 2 with the limits of 2 comma x. Upon simplification, you will get the solution as minus 3x square plus 2y cube minus 4 equals to 0. So this is more or less, this is the same as the equation 3x square plus, which equation it is? You just find out from this solution, like you will get 3x square minus 2y cube equals to 4. Okay? Yes. 3x square minus 2y cube equals to minus 4, or it's a plus 4. So you will get the solution of B. Okay. So next question is, given, again, we have a velocity field here, and the velocity field is a big equation. As you can see, V equals to 5x square y I cap plus 2y square z. It's a long equation and 3 components, x, y, z components are already included here. Whatever the velocity field you are getting in the question, you just needs to segregate the u velocity component, x velocity component, y velocity component, and then determine the local and convective accelerations along the z-axis at the point 1 comma 1 comma 1. It's a question looking like maybe a bit difficult for to understand, but the easy way to understand is two things they asked in the question. They just given a velocity field v equals to some long equation here, and they asked you to find out the local velocity and asked you to find out the convective acceleration, local and convective acceleration they asked for this velocity field. Okay, how you can do it? Before going to do that, you need to understand what is this local and convective acceleration. Suppose if you, the name itself, you can understand the local means it should be at some specific point. Suppose this is your x coordinate and y coordinate, and if you want to find out the local acceleration at some point, this is some say capital X and capital Y. I need to find out the acceleration at this point. Okay, so and the convective acceleration, and I need to find out the acceleration based upon its position. So two different. So at this position, how do you find out the acceleration? That means you need to derivative with the time. And the convective acceleration, that means the acceleration as it's changing the position from capital X1 say capital Y1. So suppose the particle is changing from this position to this position, and it has no, suppose there is no velocity change with the time, but definitely there might be chance of velocity variation with respect to spatial coordinates. Okay, that's what we called as acceleration due to the convective or due to the change in position. So how do you find out? If you want to find out the local acceleration, you just need to do dou v by dou t. Dou v by dou t means you just need to do the partial derivation of this velocity vector with respect to the time. So what are the, is there any time parameter? First you need to look at, because this is only the time involved and it is a partial derivative. So all the respective variables like x and y and z will become will act as a constant. There's no need to worry about. So only the time parameter is this one. We have only 44t. Okay. So I just remaining components. My component of x will be 0. My component of z will be 0, because if I do the partial derivative, there is no t term here, no t term here, and there is only t term here, that is 44. And if I do the partial derivative dou v by dt, this will give me only 44. Okay. So this is my local acceleration. That's it. So you got one solution. The solution can be A or solution can be C. You just need to understand the options also. You first need to look at what is the suitable option for that respective question, even if it is looking very big. If it is question is looking very big, the answer might be very simple that you can get from by looking at the options that you given to you. This works in the competitive kind of scenarios. And now you sorted out the any possible two correct answers. What is the next possible correct answer is that you can only obtain after doing the convective acceleration. Before going to tell you that how do you calculate the convective acceleration, you just need to understand the substantial derivative. Substantial derivative means, suppose if I have any variable velocity, suppose my velocity variable v is my velocity, and this is what we call the substantial derivative dv by dt, and you can write it as dou v by dou t plus u dou v by dou x plus v dou v by dou y plus w dou v by dou z. Okay, this is what we call the substantial derivative, and this is the local acceleration of this velocity, and this is called the convective acceleration. Okay, so these two are the things of the convective acceleration, but you may have get the question. I said here it is a v. V means v includes u, small v and w. But do I need to calculate this for every velocity parameter like small u, small v, small w? No, because the question is not complete yet. You just need to understand along the z-axis of the point. That means I need to do only along the z-axis. What is the z-axis means? The small velocity component w. So how do you find out that local acceleration, or sorry, convective acceleration? You just need to use u dou w by dou x plus v dou w by dou y plus w dou w by dou z. You already have the w component. That is what w component is, this last comp. The w component is your last component. Okay, 44. What is your w? W equals to 44t minus 11x y square. This is your w component, and substitute all the remaining things. U equals to 5x square y I cap plus, sorry, this is not plus, and then dou by dou x of w is 44t minus 11x y squared. You just need to substitute all the parameters and then simplify. And then if you try to simplify these things, you will get a simple solution, like a simple numerical value after substituting this point. But before going directly, I just want to substitute on behalf of you. You can take the notes of it so that you can easily understand how to solve this assignment questions later on. And W is 44t again. Please don't take the controls, don't play with the Teams presentation here. Okay, and then 44t minus 11xy square. Then what else you have? Plus again 44t minus 11xy square then dou by dou z, this is y. This is y. And then w is again 44 t minus 11 x y square. Okay, so if you simplify this, what you will get? You will get some equation again. Okay, let me erase this one. If you simplify this, what you will get? You will get the solution of 5x square y minus 11y square plus 2y square z times minus 22xy plus 44t minus 11xy square times, and this parameter will goes to 0, the last one. And then substitute the points you have. You have the points of x equals to 1, y equals to 1, z equals to 1. If you substitute that, you will get this simplification answer is 99. So the answer for this, like the local and convective accelerations are 44 and 99. Okay. Anyone has any question? Like if you have any question, you just raise your hand. I will try to resolve it now at the instant so that I don't miss the concept that you are trying to ask. Any questions? Okay. So let's move to the next question. So here we have some unknown kind of thing question is here. This unknown kind of thing does not mean the variables are looking maybe unknown to you if you are not in the background from the aerodynamics or not from the background of aerospace, but it is all simple fluid mechanics. You don't need to worry about it. This is all basic fluid mechanics that you generally see in the mechanics of physics courses, whatever it is. So the question is, a velocity field is defined as u equals to 2y square I cap minus 17x yj. In this aerodynamics of fluid mechanics nerve field, we always focus on the velocity field. How do you govern the velocity field? How do you write the velocity field? Okay. Based upon that only, you used to develop remaining all the solutions in the aerospace or the aerodynamics, all the basic aerodynamics. My velocity field is now, I write it as the 2y square I cap minus 17x j cap. This is the u component. They say it is a capital U, or you can say u, and it is minus 17x. Okay, so small u component is 2y, and v component is minus 17. This is y square, 17x. And now it's an incompressible fluid media. Incompressible fluid media means there are a good definition of the incompressible, but generally people used to say it is a kind of no density variation, but it is not complete if you say it is incompressible. If you say incompressible means that is not only the no variation in density, but are also some more interesting things are also there. I don't want to include them now here. So this is a no density variation you can take. So the density equals to rho equals to constant. And then what is asking? Verify whether it satisfies the mass conservation. If so, find the expression for the stream function. Very interesting. What he asked is, he asked to find out whether this equation is satisfying the stream function or not. Sorry, mass conservation or not. It is not stream function. It whether this equation is satisfying mass conservation or not. If you don't know what is the mass conservation, you should understand the equation and how it is derived. You will come through definitely this mass conservation derivation in these classes, and few maybe already started. I just want to write its equation instead of telling you the details of derivations of it, so that we can cover the main aim of this lecture. So what is the main aim of this lecture is just to make you help of solving the methods or to tell the techniques in solving these problems and to clear your doubts. So the continuity equation or the mass conservation equation that you write in partial differential form is dou rho by dou t plus dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w equals to 0. So any equation, any flow velocity field should satisfy this equation. That means if velocity, sorry, you have a velocity field v bar or u bar, some velocity field u I cap plus v j cap plus w k cap. U component of the velocity, v component of the velocity, and k component. So these three, if you substitute this into this equation, this governing equation, the equation should yield equals to 0. Unless it is not satisfying, this velocity field does not exist in nature. That is what the role of this continuity equation, and that's why it is very necessary. So velocity field cannot be randomly selected unless you are trying to select, or unless it is satisfying the continuity equation. You cannot say that is an existent velocity field in the nature. So now it is already given that incompressible fluid media, and we said rho equals to constant. Okay, and if your rho equals to constant, the equation is further simplified, right? How you can simplify the equation? Simplified equation is dou u by dou x plus dou v by dou y plus dou w by dou z equals to 0. This is much simplified version, because as we given that rho equals to constant. And one more thing is what else? The equation, there are only I component and j component of the velocity. This is I component and j component, and w component is 0. There is no w component of that, is there is no velocity in the z direction. Okay, if there is no velocity in the z direction, then how further it can be simplified? This is going to be 0. So the only equation that is you have is dou u by dou x plus dou v by dou y equals to 0. This is very simplified form of this mass conservation form for the two-dimensional. So now the question is asking whether it is possible to solve, or it is existing, whether it is satisfying this equation, the velocity field is satisfying this equation or not. You should able to understand, like you need to solve this. How do you solve this? Whether the velocity is existing or not. Just substitute the values of u and y component. Dou u by dou x of what is u? 2y square. Okay. And dou by dou y of what is your v? Minus 17x. Okay. And please mute yourself. Okay, now if you try to solve this, what will happen? Here it is, my variable is x, and I don't have any variable in this parameter. So it is going to be 0, and this is also going to be 0. So now my equation is satisfied. That means this velocity field exists and satisfies the mass conservation equation. Okay, this is one step that the question is asked. Mass conservation is satisfied. Yes, mass conservation is satisfied. Then the again question is, if so, find the expression of the stream function. How do you find the expression of the stream function? It is completely different type of question, like whether you solved it or not in previously. How do you find out the stream function? Basic fluid mechanics. You just need to understand what is the stream function. Okay, how do you solve the stream function is you just have to see like what is the stream function basic definition. Like if you see stream function is dou psi by dou x. Okay, dou psi by dou x, this is one part, and dou psi by dou y, this is one part. I'm not going to write anything here, just to give you the basic idea. What if the question is, my question is, stream function is psi, and you will get to know why I'm writing this dou psi by dou x equals to v. I will write it as v. Okay, this will be minus v. and I will write it as U. Okay. So now your task is just substitute this V and U again back to this main conservation equation. Substitute these two in this equation. What you will get? You will get dou by dou x of your U is dou psi by dou y. Okay. And dou by dou y of your V is minus dou psi by dou x. That is again dou square psi by dou x dou y plus dou square, sorry, this is minus dou square psi by dou x dou y equals to 0. That's it. These are two are same parameters and this is satisfying the equation. So I can write my velocity field. I can write if you are satisfying, if some velocity field is satisfying this conservation equation, this mass conservation equation, then you can write U equals to dou psi by dou y, and you can V equals to dou psi by dou x. So this is how you can write once if any velocity field is satisfying the mass conservation. So once you've done that, what you need to do, you just need to identify still the stream function. How do you can identify? Suppose take this U component. Suppose you have U equals to dou psi by dou y, right? Then I want psi equals to U dou y, dou psi equals to, and then if you integrate, partial integrate, integral U dou y, then substitute U value. As you know, U equals to 2y square. This will become psi, and if you substitute 2y square and integrate this, what you will get, 2y square and dy, this will give you psi equals to 2y cube over 3 plus function of x. There should be some function of x because this is a partial integration with respect to y. Okay, there should be some other function of x, as this is a partial integration with respect to y. So this is one solution. That means 2y cube by 3 plus f of x. Is there anything like that? 2y cube by 3? Yes, this is 1, this is 1. You can directly say the already solution identified because this is 2y cube by 3, that is plus already here. So your solution is should be A. But for your understanding, I'm going to show you the next one also. Even how do you find out the next one? You can find out the next one means the second from the second equation, that you have this part. Still you have to find out integration of this part. V you have, right, dou psi equals to minus V, and if you integrate also minus V dou x. So the same thing you will get again, minus V minus what is O, V equals to 17x, right? Integral dou x. Okay, if you integrate it, what will happen? You will get psi equals to minus 17x square over 2 plus f of y, some function of y. And you have another minus here, and this is 1 minus here. Your V component is 1 minus. That means your V itself has a 1 minus here. That is this one and this minus. This both will become plus here. So that's how you will get 17x square to y cube by 3. Got it? Okay. Now moving to the next question. Here a question is, in a two-dimensional incompressible boundary layer over a flat plate. I assume you all gone through some basic fluid mechanics. If you still don't know the basic fluid mechanics, I will give you some hints and some concepts so that you can understand the solution strategy, how you need to solve these things. And in a two-dimensional incompressible boundary layer over a flat plate, that means suppose you have a flat plate here. Sorry. You have a flat plate here and you have an incoming flow here. A flow is coming in the x direction like this. Okay, and you will see generally it's a very common everywhere. If the fluid is viscous, you can find out even any flat plate or any kind of, it's not visible, but you can see the velocity at the boundary, velocity at the wall. If you see any river, it is very common observation that the velocity at the wall of the river or the bank of the river is very low compared to the center of the river. That is because there is a formation of the boundary layer. That means as the fluid has a zero velocity on the surface, fluid has a viscosity, it attaches to the surface of the wall at this point. So the velocity slowly grows to the center of the, and this is not a center, this is some line I'm just drawing here. Okay, this is just a representation people used to do with the boundary layer, and this has a good definition, good definition of how to draw this line. This is, suppose your free stream velocity is 10 meters per second. This should be 9.99, okay, or 9.9 meters per second. Is this line, the line that you are creating is, should be, all these lines should have all the points. If you take any points on this line, the velocity should be 99% of the incoming velocity. This is your incoming velocity. And if your velocity at the particular location, if you go, here it is a velocity 0, and you have 2, 3, 4, like this, it will go to the some 10 velocity, particular velocity. The point at which you will get 99% of free stream, that will you called as the boundary layer location. Okay, the height of the boundary layer from the flat surface to the that particular location. So that is what the boundary layer basic definition, the boundary layer of the flat plate, and the x component of the velocity is given by the x component velocity. That means you have a boundary layer like this. You don't see any y velocity here. This is only x velocity. The velocity grows from 0 to 9.99 or 10 in some way, some parabolic way. You don't know this is a parabola or what way it is, you don't know. So even though you don't know, people used to try to model it by some mathematical formulations and some solving the governing equation. And here he is giving this particular velocity. That means at y equals to 0, if you substitute your y value in this at y equals to 0, you will get the velocity at this particular location. Y means if I go normal to this, this is my y direction. If I substitute y equals to 1 or y equals to 0.5, I will get the velocity at that particular point. If you just try to submit the y equals to 0 here, you will get u equals to 0. Okay, and you try to submit y equals to 0.5, you will get the velocity at that particular location. That's how this profile is varying. So velocity is increasing as you go normal to the wall surface. That is what this velocity u is stating to you. So the x component is given by this particular velocity. The distance y is measured, the same thing is repeating, and the distance y is measured along the normal direction from the plate. This is the plate, and if the flow is rotational, again the new things are coming here. If the flow is rotational, obtain an expression for angular velocity. It's interesting. So what he is asking is, if the flow is rotational, you have to obtain the angular velocity. The question itself is given that the flow is clearly rotational. What does the rotational mean? Do we need to understand the rotational mean? Yes, because as he is clearly stating that flow is rotational. And what he is asking you the angular velocity, right? So just write what is the equation for the angular velocity. The equation for the angular velocity omega for the fluids is half dou v by dou x minus dou u by dou y. You may get a question, what is this v and u? It is against your components u I cap plus v j cap plus w k cap. You don't have w here, so you can cross it out. And do you have v component here? You did not give any v component here, you can cross it out. And you have any u component? Yes, he gave the u component, small u, this is x velocity direction. And if you don't have the v component, v equals to 0, this first component will also. That means omega equals to half minus dou u by dou y. Okay, this is how you need to simplify your equations with the given information. The given information doesn't consist of v, and even if you think in the physics sense, there won't be any sorry, there won't be any significant v velocity. V velocity means a velocity that normal to the, velocity in the y direction. Okay, Now what we need to do is we just need to substitute what is the u velocity. It is a half minus dou by dou y of u equals to 9 by 2y minus 3 by 4y square. Okay. So this is the simple direct solution. If you want to try to find out the angular velocity, you just need to, if the velocity is generally they give u and v are the velocity components, generally you find out to find out the angular velocity. So that means this is the z component. You should remember this is a z component k. Okay, this is the z component k cap. These derivations all you will go through of how this omega z came and what is the background of it, what is the physics of it, what is how angular velocity is defined. All these things you will came to know in this course if you go through the lectures very carefully and you derive on it on your own. You should derive on your own. So this is what omega z. Omega z equals to, the simplified form is omega z equals to 1 by 2 minus dou u by dou y. Sorry. Just already substituted 1 by 2 minus dou u by 9 and you just derivative it. Omega equals to 1 by 2, what will happen? Minus 9 by 2 dou by dou y is y square over 2 minus, and this will give you the plus, the minus of minus plus, and the 3 dou by dou y of y cube over 3. Okay. This will, this is your form, like angular velocity form. So you just need to see, oh sorry, I think I did wrong. Here it is, it should be the derivative, not the integration. Okay. So this is equals to 1 by 2 minus 9 by 2, dou y by dou y will get cancelled, and plus 3 by 4 into 2y. You just simplify this, you will get minus 9 by 4 plus 3 by 4y. This is your solution. I hope you all understood this. Let's go to the next question. Okay, here it is a very interesting question. I like some of the questions that we are going to see here because those things will give you some idea of, instead of solving, you will also learn the theory of this, some important fundamentals of aerodynamics. So the question is, what happens when the flow over a body is inviscid according to the D'Alembert's paradox? It's very common, like every basic aerodynamics or fluid mechanics student should be able to understand what is this D'Alembert's paradox. A D'Alembert's paradox saying that suppose he tried with some mathematical calculation and he assumed that the fluid has no viscosity. Viscosity, I hope you all know, that's the effect of resistance between flow over and any body. If there is some, this is some body, if you are fluid, if the fluid is moving on this body, it will offers a resistance on this body. That means there will be a force that is called frictional force due to the viscosity of the body, and that acts an additional force on the surface. So this additional force can drag this body. This additional force can drag this body and acts as some frictional force, that is frictional Fs. That is how viscosity works. But in his mathematical calculation, the D'Alembert did something like he did not consider this viscosity and tried to solve the things in mathematical manner. He tried with a basic cylinder like this, and while he is doing that, in his calculation, he understood that the friction force Fs is equals to 0. Okay. Frictional force is equals to 0 because he did not consider that, I mean, frictional force I can say, because he did not consider the mu. Mu means the viscosity, the resistance of the fluid offering, that you can say there's a coefficient of the resistance. Since he did not consider this, he definitely will get the frictional force Fs equals to 0, as he did not know about this parabolic form of velocity distribution or the resistance offering by the fluid. So that's what we call in the basic aerodynamics that as the D'Alembert's paradox, that is zero drag. So if a body is inviscid, you will get a zero drag. That means the fluid has no viscosity or no resistance. It cannot experience any drag force due to that fluid. Okay. So let's go to the next question. Now here you have a fluid is flowing past a solid surface. Consider a fluid is flowing past a solid surface. Surface is did not mention clearly what kind of surface it is, because we need to understand the surface. So because whether it's a flat surface, whether it is a curved surface or a cylinder or a sphere or many things that you need to understand the surface, because the surface and the shape of the surface and the flow condition, I mean, what velocity the fluid is coming onto the surface or inside the surface, everything you need to understand in this aerodynamics, and then only you can clearly able to understand the physics or the modeling of that particular problem. So the flow separation from the surface may occur due to, so the fluid is flowing past a solid surface. Let me draw an airfoil. This is a common thing that you already seen in the course that you have gone through the lecture so far. Here it is there. What they are saying is, this is the solid surface. Yes, this is the airfoil is a solid surface, and flow separation occurs. Suppose if the flow is coming like this and going like this, and it is not attaching with the surface at this portion. After this portion, the flow is not attaching. Whatever the particle is coming here, it is leaving the surface and going through like this. Not yielding any kind of velocity distribution here. Okay, so this happens because of adverse pressure gradient. What is this adverse pressure gradient? This adverse pressure gradients, I hope you already came through this lecture. If not, I will just give you a brief understanding of it. Suppose you have an airfoil like this, and the flow is passing on the airfoil like this. And if you measure the pressure, suppose this is the pressure at this point, pressure at this point, pressure at this point, pressure at this point, all the pressure at every point, if you measure like this, I'm measuring the pressure from starting point to end point. This is my x equals to 0, and this is my x equals to some 10 or 20, whatever the meters, whatever the units it is. And if you measure the pressure at every point, you can see at this location, suppose this is your zero location, starting your zero location. From starting from here to here, you will see a large drop in the pressure. Large drop in the pressure, because if you see your Bernoulli equation, I'm telling in a simple manner, but science is still more in deep in this. Yes, Rohit, what's your doubt? Rohit? Okay, so if you see the Bernoulli equation, P plus half rho V infinity square, so P plus
हाँ ये भी बात सही बात है, बेचारा बहुत मेहनत कर रहा है। अरे भैया सवेरे का उठना ही।
I will write you in a simple format. P by rho g plus V square by 2g equals to, this is P1, P2 by rho g plus V1, V2 square by 2g. That means pressure and velocity are the two parameters, those are interchangeable, and those are playing with this Bernoulli equation. If you increase the pressure, the velocity and pressure, those two are playing in this equation. If you have the velocity increasing, here you see the velocity is increasing along this surface. Yes, Priscilla?
Sir, isn't there pressure head also? I mean potential head Z in Bernoulli's equation. Potential.
Potential head, that rho GH you are talking about. Or the head
No,
term.
not pressure head, potential. Z1 and Z2 on each side.
Z1 and Z2. There is a logic why I removed this Z1 and Z2. I will tell you that in a minute. Okay. And because I consider this as air. Okay. Just because of air, I removed this Z1 and Z2, and that's a good catch. I will tell you what is the reason why I removed this Z1 and Z2. So now, as your velocity is increasing on this particular portion, if you try experimenting on any kind of airfoil or any kind of surface, the flow is coming with the velocity of 10 meters per second, suppose. At this particular portion, if it is a cylinder or whatever the object, the velocity will increase to some 15, 20, whatever it is. If the velocity is increasing here, how rapid it is increasing, that much of rapidly the pressure, this is the pressure, suppose, that much of rapidly the pressure will drop here. This rapid drop in the pressure we called as, yes, Priscilla? Can you, question is done? Okay. Okay, I will tell you that. So if your pressure is like that, this is what we called as adverse pressure gradient, as because of this high velocity on the surface. And this much of pressure, as it's dropping so much, the fluid cannot hold on the surface anymore. Fluid cannot hold on the surface anymore, and the pressure in the backside of the surface, this atmospheric pressure, whatever it is, this is more pressure than this. Okay, this is because the pressure is decreasing so much here, and it is the backside of this portion, backside of it is a high pressure. In the conflict of these two, the boundary, there is some more thing like there's a boundary separation also. I'm not going to in detail of it. The flow cannot sustain anymore by attaching to the surface, and then it will suddenly leave on the top of this. So that is what we called as a sudden decrease and more drop in the pressure, we call as adverse pressure gradient. This is the term. So that's how you can see the flow separation of the surface. Okay, that is what the term adverse pressure gradient. And as asked by Priscilla, that why I removed the term Z1 and Z2 from this Bernoulli equation is, if you are considering the water, any water column or any air column, suppose this is a water and this is the air, and I'm trying to measure the static pressure at here, at this bottom surface of water and at this bottom surface of air. Do I need to understand, or do I need to include the height of this air column? Which one I need to include? To calculate the pressure in the water column, I definitely need to include this height h1, as because you rho g h1, this rho parameter is so significant, the density is so much high in the water column, and it is creating an impact in the total equation. But if you consider this in the air column, rho gh, this air of the density of the air is so much less. Say 1000, and it is 1.225 1000 kg per meter cube and 1.225 kg per meter cube. So it is a common practice that people used to neglect the rho term or the z term if they are using the air as the medium for their calculation, just to simplify the things, and it is not so significantly affect, it won't significantly affect also in the solution. Is that your doubt clear, Priscilla?
Yes, sir. Yes, it's clear.
So next, let's go to our next question. We have the question, people likes it very much who are from the mathematics background, or who are interested in mathematics very much. They like this question. It's a completely pure mathematics, like I, it's some term they given I, x, ln of x, dx. Can someone is who is interested to guide this, can someone please tell me, so that it's very interesting to solve if you are trying to teach to others also. I will just write if you tell the solution how to do it. I hope you all did this so many times. Anyone voluntarily willing to tell this? How to find out the integral x log x dx? Or any basic idea how to start it? What is the thing that we need to use in the mathematics? X log x.
The product rule.
Product rule.
Oh,
nice.
no, sorry.
Anything that specific name?
Sir, integration by parts.
Integration by parts. Nice. What's your name?
Yes.
Okay, Ayaz, good. So it is basically the integration by parts, and for this integration by parts, what we need to use? We need to use one more tool. What is this? The iLate. I hope you all, yeah, I hope you all are aware of this iLate tool. I'm not going to in deep of these things. So according to this iLate, what are the parameters you will take? And you have the rule like integral u dv equals to uv minus integral v du. This is the rule you have. So what is my u and v components according to the iLate? According to the iLate, my u component is ln of x and v component is, sorry, it's not v components. Let me, the dv equals to x dx. So just try to substitute again. So integral u equals to ln of x and x dx. That is what our question. And u equals to ln of x. And what is a v? If it is dv equals to x dx, you will get v equals to, you just need to integrate it, x square by 2. Okay. X square by 2 minus integral, again what you have, v, again you have v equals to x square by 2. This one you need to integrate, v equals to integral x dx, that is x square by 2. Okay, and then if you try simplify du, u equals to, again we have d of ln of x, differentiation of ln of x. You simplify this, just need to simplify, you won't get any by parts again, because this is d of ln of x is integral x square by 2, ln of x is 1 by x, you just simplify, this will give you integral x by 2. Okay, x by 2 dx, this is dx, not here. Okay, so finally if you simplify, what you will get, x square over 2 ln of x minus 1 by 2 and the constant plus 3. This is your solution. Okay. So let's go to the next question. Here our question is, the boundary layer approximation of Navier-Stokes equation produces the following type of partial differential equation. Oh my God, this is a too big question, but you are all aware of this. Navier-Stokes equation. How many of you are aware of the Navier-Stokes equation? Can you all raise your hand if you are aware of it? Just raise your hand to understand the count if you're like the Navier-Stokes equation or the continuity equation, Navier-Stokes equation. Just raise your hands. Okay, if not, that's okay. So let's see what are those equations you will have. In this Navier-Stokes equation, 3 important governing equations. Okay, what are the 3 important governing equations are? Let's try to write this. I'm going, so these are looking like very big equations, but if we simplify it, these things looks like very, very small things. So I just want to write for your case of understanding. So just write it, and then I will tell you how to simplify this. And with these equations, you are able to solve any kind of problems. Any kind of problems, 90% you can solve all your problems. So rho dou u by dou t plus u dou u by dou x plus v dou u by dou y plus w dou u by dou z equals to minus dou p over dou x plus mu dou square u by dou x square plus mu dou square u by dou y square plus mu dou square u by dou z square. This is your first equation. Looks like very big, but don't get scared. These are very small things, like you will see how easy it is to simplify these equations while you are doing the problems. So rho dou, this is a v component. just have a note of these equations I'm writing here. You'll be able to solve all the problems with this.
Integral of what?
No need to remember this. Sorry? Who is that? Okay. And this is u dou v by dou x plus v dou v by dou y plus w dou v by dou z. That will give you minus dou p by dou y. Just try to understand how similar these equations are. Like every equation has a similarity with the next equation, like that you can say. Dou square v by dou z square. You don't need to remember this. These are all similar. Dou u by dou t. This is dou v by dou t. U, v, u, v, u, v. P component, P component. And the last one, dou w by dou t plus u dou w by dou x plus v dou w by dou y plus w dou w by dou z equals to minus dou p over dou z plus mu dou square w by dou x square plus mu dou square w by dou y square plus mu dou square w by dou z square. These are the three important equations that one should remember while solving any kind of important problems in this Navier-Stokes equation or in this kind of boundary layer problems. Okay, so I'm just if you take the note of it, I am going to erase all these things and I will go to the solution of this question 9. I'm erasing it. Okay. Now the question is the boundary layer approximation of a Navier-Stokes equation produces the following type of partial differential equation. The partial differential equation that you are trying to solve is the Navier-Stokes equation. That's what I wrote all these questions, that you need to understand what are those partial differential equations, how those things actually solved. Suppose this is the boundary layer that they given us, the boundary layer approximation. Okay. If you are doing for the boundary layer, you don't need to get all those equations. Only the first equation is sufficient for you. What is the first equation? That is rho. Just let me write the equation here and you will see how you can be simplified that. So this is how the first equation is, we wrote already and I just repeated here again. So if this is the first equation and they are asking is what is this type of the partial differential equation, how you can identify different types of partial equations, what is the basic rule for it. We want to find out that the general form of the partial differential equation to identify the things is dou square pi by dou x square, b dou square pi by dou y square plus c dou pi by dou x plus d dou pi by dou y plus e equals to 0. You have a variables and this is also partial equation, partial differential equation, and the variable is pi. The pi can be anything, u, v, w, anything can be pi. So if this is the general format of any partial differential equation and you can identify the type of it, the type of it means how these types differences will helpful in solving these equations later on. So we are not going in deep of it, how this will helpful. So how it is, how you can define what type of equation it is. If your b square, this is the coefficient of this dou square pi by dou b square minus 4ac, this is a capital A c, is greater than 0, then it is hyperbolic. And then b square minus 4ac is equals to 0, then it is parabolic. And if you have b square minus 4ac is less than 0, that is elliptic. Okay, now if you see the equation here, it is only x and y parameters. There is no z parameters that are given in the standard or general form of the partial differential equation that you can identify. Since it is a boundary layer flow, we have already discussed several times how it is boundary layer flow exists. You can cancel out various parameters in this. First, suppose first one you can cancel out is this z component. Directly you can cancel out the z component and w component, because in the boundary layer flow, this is your flow, sorry. This is your flat plate and this is your boundary layer. You don't have a velocity in the w direction. That means perpendicular to the plane of writing. If I'm writing through this plane, there is perpendicular to this plane of writing, whatever to this plane, there won't be any velocity that is w, and there won't be any velocity that is going through this. That means passing into the wall of the surface or wall of this plate. So v equals to 0, that means this term equals to 0, w equals to 0, that means this term equals to 0. Okay, and there won't be any unsteadiness. They did not give any mention, they did not mention anything about the unsteadiness, so you will get dou u by dou t also 0. So you just cancel out all these parameters. What you will left, you need to cancel out many parameters here, because if you see your variation of velocity on the surface, you will have dou u by dou y as a dominant component and dou u by dou x. This is very less. Dou u by dou x is very less. Okay, if this is very less, dou u by dou y is very small one, you can cancel out these parameters also. In the similar way, what are the parameters that you can cancel out? If dou u by dou x is also very small, this one is also can be cancelled. And dou z also we don't have any variation, so you can cancel out this. What do you left? You left with only 0 equals to minus dou p over dou x plus 2 dou square u by dou y square. Okay. So this is what the simplified form of boundary layer equation. If this is your simplified form of boundary layer equation, now what is your parameter? You can ask yourself, like, this is a form that is very simplified, and now how you can define whether it is parabolic or whether it is elliptic. Just try to figure out d square u by dy square. That means my b equals to mu. Okay, and dou p over dou x. If these two parameters are different and b equals to mu, do you have any this parameter c? You don't have any c here. No, sorry, c equals to -1, you can say. And do you have any a variable in this equation? In this equation, there is no dou phi by dou x square. Any term that is not representing that is dou phi by dou x square. So a equals to 0. That means your mu equals to 0. That means equation itself is stating as coming to be 0. That means your equation is your equation is a parabolic kind of format. Okay. So next question is, pressure drop for a laminar flow pipe through is proportional to, okay, is a flow through an internal object. Suppose you have a pipe like this. Okay, and in this pipe, you have the flow here. So what he is asking is, as the flow is going through this pipe, you will get a pressure drop because of the resistance offered by the fluid. How do you get this pressure drop? And what is this proportional to? The direct question, the direct answer for this question is, you will get the pressure drop by square of the velocity, Vf. If the velocity is the Vf of the flow field, the pressure drop is proportional to Vf square. And I will give you the basic idea how it is doing. Like if it's the pressure drop, that is delta P, the change in pressure, I can say from this point to this point, it is the P1 point and P2 point. The change delta P is equals to friction, resistance of the friction into half rho u infinity square. Okay, and L by D. This half rho infinity square we call generally as the dynamic pressure. If you multiply this dynamic pressure with the resistance, frictional resistance, so you can clearly see in this pressure drop equation that delta P is proportional to U square. Got it? So this is still some more interesting idea behind this pressure drop that we can figure it out upon at the end of this session if we have some time. That again comes with the Navier-Stokes equation. Okay, so let's go to the next question. Our next question is some more mathematical. You need to try to have some idea of how this pressure coefficient, like how this normal vector concept or the surface of the conical this works, or you need to have idea of vector calculus like this. So these basic vector calculus of mathematics also you will see in this course, already that you are, I think you are learning. The thing is, find a unit normal vector n of the cone of revolution z square equals to 4x square plus y square. This is the cone that is generating that your z is equal to 4x square plus y square. And he is asking a unit normal vector n cap at the point p of 1, 0, 2. How do you find out? If you have any, suppose any function or any surface like this, you need to first clear it like this. Function of f of y, z, equals to 0. Okay. And then these are the steps that you need to identify, that to identify the unit vector at particular point. You first need to segregate the function like this, f of x, y, z equals to 0, like that you need to segregate. And then you need to identify the gradient of the function del f, that already we can call as gradient of f. That's how you can write. Okay. Then the formulation of this unit vector n cap equals to gradient of, or grad, we call this grade or gradient of f by modulus of, they both are same, grad or gradient are both are same. So gradient of f by gradient of modulus of gradient of f. That's how you will get the unit vector. Suppose, how do you find out this? You have your equation is z square equals to 4 of x square plus y square. What is your task? Your task is to rearrange this according to the function of f of x, y, z equals to 0. So that how you will rearrange it. 4 of x square plus y square minus z square equals to 0. This is my function. So how do you find out the gradient? What is the formulation for the gradient? Gradient is dou by dou f. F means f of x, this function, whatever the function is, I cap, plus dou by dou y of f, k cap, plus dou by dou z of f, k cap, equals to 0. This is what the gradient function. Okay. So now you understood what is the gradient, and how you need to proceed for this is just need to substitute your f. This is your f. Substitute this f into these equations. If you substitute that f into the equation, the first thing you will get is dou by dou x of 4 of x square plus y square minus z square. What you will get? You will get just 8x I cap. And the second thing, dou by dou y of, again, 4x square y square minus z square. What you will get? You will get 8yj cap. Okay. The same way, if you simplify for the dou by dou z of the same thing, the same function, you substitute and simplify it, you will get minus 2z, this is z, 2z k cap. This is your gradient of f. Okay. So now you have your gradient of f. What is your gradient of f? 8x I cap plus 8y j cap. Okay. Plus of minus 2z k cap. This third component is a minus. This is minus 2z. So this is your gradient. What you need to find out? You need to find out the unit vector. The unit vector is this velocity by this vector by the modulus of it. What is the modulus of it? Modulus of 8x I cap plus 8y j cap plus minus 2z k cap. You can get it by 8x whole square plus 8y whole square plus minus 2z whole square under the root. Find out this one in simplification and then just divide the both. 8y j cap minus 2z of sorry by 8x whole square plus 8y whole square is minus 2z whole square. So we just find out these two and divide and substitute the point that given, point 1, 0, 2. You substitute this point and you divide this two, you will get the unit vector as this one, 2, 2 by root 5, 0 and minus 1 by root 5. This is the simple substitution and solving of the algebra. So this is how one should find out the unit vector at any point of the surface. You just need to find out the gradient and then substitute the point values there. You will get the unit vector. The next question is a stream tube. Question: what is a stream tube? The question is given as a stream tube and given as a left. That means you need to fill it. Is a tube to transfer the fluid between different sinks and source? I don't think that you come across this source and sink. Suppose if there is a point here and the fluid is emerging from this point to radially like this from all these directions. This will be called as source. Okay. Mathematically, there are good definitions also of it, but I'm just giving the phenomena or basic idea of it, how the source is. And the sink is all the fluid particles comes to the same position, the reverse direction. This is the direction of the flow. Fluid velocity, all the amount of fluid velocity will dump at this point and it will disappear like that. All the fluid amount will start from here and it will go disperse radially from this point. This is what we call as source and this is what we call as sink. So if you see, there is no connection of stream tube to between the source and sink. So this is not the first option. And the second one is a tube to extract a fluid from separate sources to transfer a single sink. This is not also the option. And is a surface. A stream tube is a surface in a flow field formed by streamlines. This is called stream tube. This is the surface. Suppose if you have a ring here, you drawn an imaginary ring in the flow field and starting your streamlines on this ring like this. If you draw all your streamlines starting from this ring and you again try to join all these points at some particular points like this. Whatever the velocity or whatever the stream tube that you are getting, or this tube or this surface, this is called stream tube. This is basically the surface created by all the streamlines in the flow field. That is what we call as stream tube. Okay. And next thing. Incompressibility condition of the flow field in which the velocity vector is defined as v bar. Incompressibility, we already seen what is the continuity equation. The continuity equation as simplest form that I will write as dou u by dou x plus dou v by dou y. No, let me try to clearly write this entire equation so that you will understand the beauty of this question. Dou rho by dou t plus dou rho u by dou x. This is the mass conservation equation or the continuity equation, you can say. I already we already discussed this about this in previous. So I'm just rewriting this again. Okay, this is the continuity equation or the mass conservation equation. The question is incompressibility condition of the flow field in which the velocity vector is defined as. So if you see very carefully, incompressible, that means rho can be taken as constant. Rho by dot t, this will goes to 0 and all the rho will come out. So this is x, this is y, this is z. All the rho term will come out, and if you transfer this rho term to the right hand side, this will simplify like a simple equation like this. If you are aware of what is a divergence of a field, velocity field, divergence of any vector field, it is dou by dou x plus j cap dou by dou y plus k cap dou by dou z times u I cap plus v j cap plus w k cap. I hope you are aware of this multiplication, how to do this multiplication. You just need to multiply 1 to 1, and after multiplying 1 to 1, what happens to this unit vectors? I cap dot I cap equals to 1, j cap dot j cap equals to 1, k cap dot k cap equals to 1. So this equation, if you multiply, after multiplying this, what you will get that from the divergence del dot v bar, what you will get? Dou by dou u by dou x, dou v by dou y, dou w by dou z, which is the same as this right side equation. That means I can write this right side equation as del dot v bar equals to 0. So if the fluid is incompressible, the incompressible condition is applied, you will get del dot v bar equals to 0. Okay, this is a beautiful equation that you should understand. Should remember every time, and you should apply during this entire course. And this is a direct solution. That the question that we are going to see is a direct solution from your basic physics from 6th to 7th classes standards, that you can easily understand what is the kinetic energy of a body having mass of 40 kg moving with a speed of 100 meters per second. This is the question. That means there is a mass m equals to 40 kg and speed velocity v equals to 100 meters per second. Mass equals to 40 kg, velocity equal to 100 meters per second. What is asking is just asking the kinetic energy k. If you want to find out the kinetic energy k, you just need to apply the k equation. K equals to half mv square. If you simplify it, you will get the solution. Just multiply the algebra. Half mv square, 4 times 40 times 100 square. Okay, sorry, this one. This one or the solution A1, I guess. Sorry, these are not these two. Okay, so our next question is, what is the formula for a dynamic pressure? I'm sorry. What is the formula for the dynamic pressure? I will directly tell you the formula is half rho v square. But if you want to understand what is this dynamic pressure, you need to go through the lectures, and you still have time to explore this dynamic pressure concept very detailedly. But I will tell you in a simple manner. Suppose you have a flow field like this, and if you are trying to measure the pressure at some point here, the point P1, and if you can find out two pressures. One is total pressure, another one is static pressure. This total pressure and this static pressure, how it is defined? Total means say PT. PT equals to PS plus P dynamic. In the physics sense, or the by the way of like in the commonly you can see the static pressure is pressure due to the presence of matter. As a virtue, as a result of the matter exists there, there should be an existence of its property. That is what we say as a existent due to the matter, the pressure because of the matter is exist there, that we are terming as the static pressure. Then what is this dynamic pressure? This dynamic pressure is the pressure because of the velocity and the density of the fluid, or you can say because of the momentum of the fluid presence there. Because of this movement of the fluid, you will see also additional pressure that is called the dynamic pressure. That is what we call as total pressure is always like static pressure and the dynamic pressure. This dynamic pressure is derived as half rho V infinity square. You can find out this derivation by Bernoulli's equation also. Okay. I will. It is easier to further understand from the Bernoulli P by rho g plus V square by 2g equals to P2 by rho g plus V2 square by rho g. Suppose if you have no velocity here at the point, some point, you will get P2 itself is a P static. That means P static at pressure and the total pressure is same at that point if your velocity is 0. Okay. So P total, this means at some point, you have 2 points, point 1 and point 2 here. If your point 2 has no velocity, that is V2 equals to 0, then this equation will goes to 0, and the P static here, the static pressure, whatever the static pressure here is, that will become the P total. P static equals to P total, right? So P total by rho g equals to P1 by rho g plus V1 square by 2g. And if you try to simplify this, g will cancel out and the rho will come to the other side. This is P static at point 1. This is the P static at point 1 plus half rho V1 square. Now you clear, right? If there is no velocity at some particular point, that P total is equals to P static plus half rho V1 square. This is how the dynamic pressure comes into the picture. Okay. Now let's go to the next question. In a study flow, path lines, streamlines are, I already defined what is the path line and streamline in the starting at the beginning of this lecture. So in the study flow, the path line and streamlines are coincident. Okay. Path. Yes.
Can you please send all these questions by mail, sir, later?
I will share. And
Yeah,
people
with
team.
by taking the answers also, because actually this is a quite a different subject for us. We are architecture students, actually.
Okay.
So we don't have much of mechanics and all the dynamics of what you're talking. So it's a little difficult, I'm feeling.
Okay. So this for the architecture, yes, I can understand. You need to have some idea of fluid mechanics that generally mechanical people or any other branches that undergoes. If you go through that course of fluid mechanics, then it is much easier to solve this. But you are directly trying to understand this. That is also perfectly all right. As you are going through this course, you will come to know all these variables at the end of it, the session. I will share these things and solutions also with you.
This fluid mechanics subject, I thought it will be something about drawing. With urban services, what I thought maybe about the water supply and to the whole town planning kind of a subject. So I thought it will be something like that.
You're in which course? This is the fundamentals of aerodynamics.
No, I have done architecture masters.
Okay.
Master of architecture. So our subjects are different, yeah.
Okay, yeah, I understand.
But I have done in urban planning only. So I thought urban services will be something related to that through drawings like that. So I'm finding it a little difficult. Maybe with answers, if you send it, I may be able to study. Can you send some little bit of notes also, if possible?
Sure. I will send all these things. You will get the links of all this content and questions of solutions also. And then next question. The point where fluid comes to rest is called, we just discussed about the total pressure and the static pressure, right? The total pressure is PT and the static pressure is PS plus dynamic pressure PD, and we have 2 points P1 and P2. Suppose you have a velocity at point 1, this is point 1 and this is point 2. You have a velocity v1 and point 1, and there is no velocity at point 2. Okay, if you don't have any velocity at this point 2, your pressure will come to total pressure. That means the pressure at point 2 is total pressure, or this also we called as stagnation pressure. This also we called as whatever the total pressure, if the velocity is becoming 0, we called as the total pressure, also called as stagnation pressure. But ensure that you have a free velocity at before this point, like this is a velocity, there should be some finite velocity. Then only you will call this is a stagnation or total pressure. So if the velocity is coming to be 0 here at this particular point, maybe because of presence of some solid wall or something else, then this we called as stagnation point. Okay, point where the fluid comes to rest is called the stagnation point, and the pressure corresponding is the stagnation pressure or the total pressure. Okay, and next you have Bernoulli equation. Bernoulli equation is only valid for, I'm not going to detail of derivation of this Bernoulli equation. Bernoulli equation is only valid for incompressible and inviscid fluid. You just try to write down the equation P by rho g plus V square by 2g. If you want to include the z also, you can include E2 by rho g plus V2 square by 2g plus z. These equations are very good if the flow is inviscid. That means the flow is always parallel in the pipe flow. There should be no like resistance offered by the fluid at the walls. If these two are the walls, there should be no resistance offering by the wall. If the resistance is offered, flow never be parallel like this. Flow is always like this. That means it's here is the velocity equals to 0, here is the velocity equals to 0, like this. Okay, and here your rho should be constant. The both time you are not using rho 1 rho 2. See, here it is p1 p2, but you are not using rho 1 rho 2. Here you should have rho as a constant, that means incompressible. And inviscid, by your inviscid, you can see nowhere there is a presence of mu term. Mu is the resistance that I already told you, resistance offering by the fluid. If there is no mu term, the flow should be inviscid. That's how you define your equation. So now we are at end of this today's session. We have covered all our questions so far. Yes. So these are the questions for today's lecture. If you want to know more about, or if you have any doubts from the session of fluid mechanics, you can ask. In 10 to 20 minutes, we can cover this. Any questions so far? The session open to the questions.
Sir, can you elaborate a bit more on Navier-Stokes equation?
You want to know more about the Navier-Stokes equation? Okay. Navier-Stokes equation, all the derivation part you will come to know, but let me see, where did I write it? Yeah. See this first part. This Navier-Stokes equation consists of three equations basically. That is for the x, y, and z. That is the clear definition is the conservation of momentum, or the conservation of the momentum. How you can say? Suppose if you have a force F equals to m into a. What is this law? This is clearly a Newton's law. Force equals to mass into the acceleration. Based upon this law, the Navier-Stokes equation is also derived. But because why you have three equations? Because you have the acceleration. A is u I cap plus v j cap plus w k cap. So acceleration is there in u direction. That means x direction, v, and w also. So you have the acceleration in all three directions. You will get acceleration of on this equation. That means fx equals to max, fy equals to may, and fz equals to maz. Okay. So this is why you get the three separate equations for the acceleration and force conservation. what are the force terms you include? You have the force terms like pressure force, force due to the pressure at the surface, plus force due to the skin friction drag or the resistance of the body, or I can say viscosity, force due to viscosity, that is mu, you can say. And then you have mass. Mass, you can say it as a rho into the volume, or you can say, you just suppose per unit volume, you can neglect, or say volume equals to 1 unit. And then you have acceleration term AX. These are the terms included in your Navier-Stokes equation. This pressure term Fp will come as dou P over dou X, whatever it is, dou P over dou X or dou P over dou Y, dou P over dou Z. The differential equation, I'm just giving you the basic idea of the formation included in this Navier-Stokes equation. So the pressure term, this is how, after simplification, the pressure term remained in the equation of the Navier-Stokes, plus, and the skin friction term included with three special components, that is dou square u by dou x square plus mu dou square u by dou y square plus mu dou square u by dou z square. So this is how, this is skin friction or due to the viscosity of the fluid. Viscosity of the fluid, as I said, there is a drag or whatever the resistance of the fluid, that is also one force. So conservation of these two forces, summation of these two forces will remains or will yields your remaining momentum, that is mass into the rho terms, that is includes the mass, and acceleration is AX. How you can define your acceleration? AX equals to, suppose if you want to find the acceleration x direction, this is dou u by dou u by dou x, sorry, dou u by dou t first, because the local acceleration will come first, and u dou u over dou x plus v dou u over dou y plus w dou u over dou z. This is what we call the substantial derivative, or the acceleration. You can write like this, as the acceleration depends on x, y, z and time parameters. This is how we write according to the chain rules. You can find out this about this substantial derivative in your basic mathematics. So combination, if you combine this parameter and this right hand term on these terms, just summation of left hand terms and right hand terms. That is what I wrote as a Navier-Stokes equation in the first. Is this equation? This one. This is the Navier-Stokes equation in the x direction. Okay, you got it? Who asked this question?
Yes, sir. I got it.
You understood like how it is, what is the basic idea behind this Navier-Stokes equation? It is just a momentum conservation. Pressure term is there, skin friction terms is there, and acceleration terms is there. Yes, Arhit? Arhit, what is your question? Do you have any question? I'm unable to hear you. Okay, any other questions? Any other questions so far? And if you don't have a question, some people are asking in their doubts in discussion forms of this question. If you have the same question, or if you know the answers of it, you can also kindly reply to them, or if you have the same question, you can ask those questions in this lecture sessions every week. Okay. So any doubts or questions? We have a few more minutes left for this today's session.
Sir, in the ninth question, the value of mu is equal to 0, right? Is that because velocity is negligible or very less?
No. In this formulation of this question, I will give you clear instruction of the solution of this equation, like how it is derived clearly, as I wrote things very clumsy here. This is the basic idea of how you identify the partial differential equations and their categorization. But here the term that mu equals to 0 is not a perfect solution for it. I will give you the clear instructions, like how to solve this in a solution format. I will send you it. Some more details I need to mention here. not able to clearly confine all these things here. But mu should not be like you can state as a 0. Mu has a certain parameter as this certain value as you have fluid as a viscosity here. Okay. I will give you the detailed procedure of it, how it is happening.
Okay.
Any more questions? Any more questions? Okay, with no questions, I'm going to end this session. We can meet. So I hope I will meet you all on the next Friday. Thank you all.
Thank you, sir.
Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you.
Thank you, sir.